Yeah. I did it 4 times and I was like, it's just not even that. My answer is part A. I'm pretty sure all my answers never ever going to be like 8,000. No, this one was hard. This homework, besides the exam where we didn't have the number 6. There you go. Now, yes, now I have that. They went directly into the notes. Yeah, I have like more. I know I looked it up. But not having it. But I mean, I guess I could have assumed that it needs pressure to be. Yeah, but then only if you assumed it that way, you would have had initial. Yeah.
All right. So we'll go ahead and get started for today. So, right, as a reminder, homework is due today. Right, so hopefully you brought your homework here. Right, for those who are online, make sure to submit it before the end of class. Let's see. So on Monday, we're going to be finishing up kind of, how would I phrase it? Sort of our like introduction to thermodynamics in terms of, you know, once we kind of finish Monday, we'll have talked about the different thermodynamic quantities, some of the kind of properties and relevant equations for them, in a more general situation. And we're going to start talking about more specific things starting Wednesday next week. We're going to talk about phase changes and phase diagrams, systems, talk plenty about chemical potential, chemical equilibrium, talk about electrochemistry. So we'll talk about a lot other aspects of chemistry, right? Using kind of what we've discussed and done in you know, these first kind of, I guess if you've been reading the book, right, the first 3 chapters in the book, chapters 1, 2, and 3, right? 1 had just kind of stuff about the gases, real and other things like that. Chapter 2 started talking about, right, internal energy, heat, work, and such. Chapter 3 here, we've been talking about entropy, Gibbs free energy, Helmholtz free energy, and so on. Okay, right, and you know, we've been applying these concepts and principles to expansions and compressions of gases, chemical reactions, and things like that. So we have been using thermodynamic concepts for different things, but you know, starting kind of next week on Wednesday, we're going to be start kind of applying a lot more of these concepts and ideas to different problems in chemistry. Okay, so right, and so I know especially some of stuff for lectures today and Monday. Sometimes it seems like we're just kind of throwing out a bunch of information, and in some ways, to be honest, we are. We're kind of introducing, you know, these are these different thermodynamic quantities, these different things we can use to describe our system, okay? And these are different ways we can calculate it, calculate how they change, and other such things. And so, yeah, so then, you know, we try to then put some of these things in context of, okay, let's apply this to specific applications as we go throughout the semester. Okay? And kind of before we get started doing some stuff today, are there any questions people might have about, I guess, anything in the class.
There's no time limit on the quiz this week?
Yeah, so one of the comments someone had was about the participation quiz, wanting kind of potentially more time or things like that. So I said, whatever, I'll just put no time limits on those things. Okay. So now, yeah. Everyone phrases. So I originally put time limits, one, to have it kind of reflect a little bit more of how things work in class. Typically, I'd ask these type of questions in class, and people would work on it and give their answers. Now, in class, people would often work on it more together than potentially what you guys are doing online, answering these questions, right? Which and so you are welcome to work on things together. You're welcome to use whatever notes and other resources you have, but I'd still prefer you not to go to something like CHEM and ask the question and wait for someone to give you the answer or something like that, right? Which is, I know, a thing that can be done. And I mean, I don't worry so much about stuff like that in this class as I do in my general chemistry class, which I have found questions in my general chemistry class up on Sheets. But yeah, all right, but if people want to discuss questions, discuss answers and things like that, they are welcome to do so on those participation questions. But yeah, so I might put back another time limit, but I might make it like a fairly long time limit or something like that. I don't know. So I don't know how it works. I guess if there's no time limit, can you start and stop taking the quiz? No. Okay. Once you start it, you gotta. Okay. You close that terminal, that session. Okay. So if you if you left the web page, then it would stop the quiz. I mean, like leave the web page. I mean, like say shut off your computer, right? Yeah. Okay. Yeah. So it's not that you can start it and then come back later unless you happen to have the connection lasting or something. I see. All right. But yeah. So I mean, I don't know. Maybe I'll put some sort of time limit on it, but make it like an hour or whatever. I don't know. We'll see. But yeah. So that is something that was done on purpose, not on accident. Other questions? Right, and just like the homework, right? Homework, people are more than welcome to work with each other, right? Use whatever resources they can find. Prefer you not to try to just look up the answer if there's potentially an answer for the question out there, right? Because again, the idea of the homework and why. So when I first taught this class, the homework was never due, was not worth any points. The only points in the class were participation and exams, and that was it. And I also did 5 exams, which is how the person originally had it, again, when I first taught the class. And I didn't like that because, I mean, there's a large chunk of people who just didn't bother doing the homework. Because if it's not due, why do it, right? And then there's a large chunk of people that were completely unprepared for exams. And so again, this homework is assigned and due and graded, not because I enjoy grading the homeworks and doing that by, grading those things myself, but because I view it as a valuable tool in, preparing you for the exams, as well as helping you retain the material and understand the material that I covered. So people are, attempting and putting forward their best effort in answering the homework questions, not just trying to look up some type of answers. Because some questions I give are questions from the book. I take questions out of the book. Some book online, right? People to look up the answer. So, but yeah. So anyways, so I and we'll just reiterate that I really hope people are doing their best at attempting the homework, and then looking over their homework and the answers and other things like that when preparing for exams. Okay, it's a very good place to go when trying to study for exams. Other questions?
Are we supposed to go online to find the equation to question 6 on the homework? Should we not go over it in class?
What was, I got to look up question 6 real quick on the homework here. Homework 3. Question 6. Calculate delta S on 2 moles of a diatomic perfect gas for which Cp equals that. This change from 25 degrees Celsius and 1.5 atmospheres to 135 degrees Celsius and 7 atmospheres. I'm not sure what equation you used for this. So for question 6, what equation did you happen to have to say look up and use? So there, I mean, wasn't necessarily right. So in this problem, so question number 6, you had something where temperature. Here, let me swap to this, right? Right. Question number 6, you had a situation where you had some initial temperature, some initial pressure, some initial volume, right? And you go to some final temperature, final pressure, and final volume, right? In the problem, you're told the temperature change and the pressure change, right? So you're given these quantities, right? And you're asked, what is delta S, right? Should I have this focus a little? Sort of. Zoom out a little bit. A little bit more. Yeah. All right. Right. So you're asked for what delta S is, right? In this case, right, all 3 things are changing, right? So this is a irreversible, and it's obviously not saying it's done reversibly. So this is an irreversible process. 3 things changing. So I got to find a reversible pathway. Okay. And so my reversible pathway, I could do a constant temperature process and then a constant pressure process reversibly, right? So constant temperature to change T initial to go to the P final, okay? And then Vx, right? And then a constant pressure process where I go from initial temperature to final temperature, right? And then for this, right, this is NR, LN, constant temperature. No. It's constant temperature is NR, LN, and then we wrote this as V final over V initial, right? But the thing is, we don't know what V final and V initial are. You can either calculate those using the ideal gas law, PV equals nRT, right? Because you have the temperature, you have the pressures, right, that you're going to. Or you can use the fact that P initial over P final ends up equaling V final over V initial, again, from the ideal gas law, and plug that in there, right? And then here for the constant pressure process, right, you have just Cp M, then Ln T final over T initial, right? Yeah. So, yeah. Okay. Right, and so this is, one of trickier problems, right? So there's, different types of problems we can be given, right? So a simpler version of this problem is, instead of giving the pressures, right, you're given the volumes, right? Let's say you're given the volumes and temperatures, right, in the problem, okay? Then, it's like, okay, NR, LNV, final V initial, right? Just plug and chug, right? Once you kind of identify the relevant equations, right? But in this problem, because you're given the pressures, there's sort of this extra step, right? That either I can use the ideal gas law to calculate the volumes, right? Or I can, use the ideal gas law to get to this relationship here, right? Right. So, so just keep that in mind. Even I think there's probably one problem on the exam at least, right? Where, often you're not necessarily given every single pressure, volume, temperature, for your initial and final states, but you're given 2 out of the 3, and you can always use the ideal gas law to get that third, right? And so that's a very common thing that happens in plenty of problems, right? It's not necessarily designed there just to trip you up, but also, because the fact is you measure certain things in lab, right? You're not always measuring like all temperature, pressure, volume for all things, right? You might measure just some of those things, and then you need to always calculate the other one in lab, right? So, but yeah. Other questions? Confusion about the homework. All right. Well, let me open up the chat here. I have no idea if people said anything. Zoom chat. Nope. All right. All right. Okay. Questions, comments, concerns? Okay, so let's continue discussing Helmholtz-Gibbs free energy. Okay. Here, we did this last time. Yep. All right. Talked about that last time. Did we talk about this question last time? No. Okay. All right. So we'll start here, and we kind of started some of this lecture last time was talking about some stuff with Gibbs free energy. So, right. So here I have an isothermal constant volume process that is near 0 Kelvin. Which of the following quantities is most important in determining whether the process is spontaneous? Is it, and again, right there, if there's no subscript, right, all of these things are referring to the system quantities, right? Enthalpy of the system, entropy of the system, Gibbs free energy of the system, internal energy of the system, right? They're not of the surroundings, not the universe or anything like that, right? These are all for the system, right? They would be, you'd see like subscript surroundings or subscript universe to tell you we're interested in the surroundings of the universe and not the system, right? So yeah, so which of these thermodynamic quantities, or maybe they're all equally important in determining whether or not the process is spontaneous? For an isothermal constant volume process. So here, B, discussion of potential entropy. Any other D's, internal energies?
I just don't know really I would say.
Huh?
I mean, it's isothermal, so delta H and delta U are something 0. If it's near 0 K, then delta F is a product, and that's very important as well.
Yeah, so for here, we don't know, right? It could be a constant volume isothermal process that involves a chemical reaction, phase change, right? So we don't necessarily know the values of delta H and delta U and delta G and things like that, right? It those could be non-zero, right? Because it could also be for a non-ideal gas and things like that, right? But so what some people are getting at, right? The thing to think about here, right? If I want to know if something is spontaneous, right? in general, right, the second law of thermodynamics tells me if something is spontaneous, the entropy of the universe is greater than 0, right? But again, we don't want to measure the entropy of the universe for every single process, and so that's where we came up with the Helmholtz and Gibbs free energies, right? Those are pure system quantities, Helmholtz free energy and the Gibbs free energy of your system, right? And under constant temperature and volume conditions, the Helmholtz free energy is just negative the entropy of the universe, and under constant temperature pressure conditions, the Gibbs free energy is minus the entropy change of the universe, right? So under constant temperature volume conditions, Helmholtz free energy tells you about spontaneity, and under constant temperature pressure conditions, Gibbs free energy tells you about spontaneity, right? And so in this case, we're under constant temperature and volume conditions, which means Helmholtz free energy will tell us about spontaneity. The Helmholtz free energy is defined as the internal energy plus temperature times entropy. And so a change in Helmholtz free energy under constant temperature is just equal to delta U plus, or sorry, minus, not plus, delta U minus T delta S, okay? Right. Yeah, so again, right, because we have constant temperature and volume, that means under those conditions, the Helmholtz free energy A is related with minus delta U, or delta S of the universe, sorry, right? Okay, which, right, just basically saying that, hey, this tells you about spontaneity, right? That something's being spontaneous is related whether or not the Helmholtz free energy is less than 0 or greater than 0, okay? And so, and then again, a change in our Helmholtz free energy is related with the change in internal energy minus temperature times the change in entropy, okay? Under constant temperature conditions, okay? And so under constant temperature, if temperature is near 0, then this term is effectively 0, right? And so it's mainly just that internal energy that's going to determine whether or not your process is spontaneous. So if the internal energy change is negative, the process will be spontaneous. If the internal energy change is positive, then it will be non-spontaneous. Questions about this question here? Again, when thinking about this question here, we first have to think about, well, what tells me if something is spontaneous, right? Well, entropy of the universe, you know, what else? Well, Helmholtz free energy or Gibbs free energy can only under constant temperature volume or constant temperature pressure conditions. Okay? So for constant temperature volume, I know the Helmholtz free energy can, and then I have to just think about, well, how is the Helmholtz free energy related with these thermodynamic quantities? Okay, and that's how we get D here, delta U. All right. So which one of the following combinations is consistent with a pressure process that is spontaneous at low temperatures, but not spontaneous at high temperatures? Is it B or D or both? D. D. Delta.
Yeah, dairy, duck, Dave.
Right, so number of people saying D here, right? So again, constant temperature, pressure, conditions, something is spontaneous, right? How we can learn if something is spontaneous under those constant temperature, pressure conditions is if we consider the Gibbs free energy, right? Again, under constant temperature, pressure conditions, delta G tells us about spontaneity, okay, which is related with delta H minus T delta S, right? So again, this is only under constant temperature pressure conditions, right? If I don't have constant temperature pressure, Gibbs free energy tells me nothing about spontaneity. I can still measure it, I can still calculate it, but it doesn't tell me about whether or not the thing is spontaneous or not, right? Right. So if I had a chemical reaction that took place not under constant temperature pressure conditions, right, then the Gibbs free energy does not actually tell me if that chemical reaction is going to be spontaneous, right? It just so happens that, the majority of the time we do any chemical reaction that's under constant temperature pressure conditions. So the Gibbs free energy is a very good measure of the spontaneity of that reaction. Okay. Right, and so here, right, we know, see at low temperatures, it is spontaneous, right? And at high T, it is not spontaneous, right? I believe that's what was given in the problem. Okay. Right. So again, if I think about this situation, right? Okay, temperature being multiplied by entropy here, right? So low temperatures, right? You can imagine temperature, say, going to 0. So this is irrelevant. So at low temperatures, my process is spontaneous. Well, that tells me at low temperatures, delta H is what's determining spontaneity. So delta H has to be less than 0 because delta G, right? Something that's spontaneous means delta G is less than 0. Yeah. Spontaneous process will have a negative Gibbs free energy change. So delta H has to be less than 0. And then at high temperatures, it's not spontaneous. Well, at high temperatures, right, this T delta S is going to be most important. And so delta G at high temperatures is roughly going to be determined by negative T delta S. And if it's not spontaneous at high temperatures, delta G has to be greater than 0. So if delta G is greater than 0, that means here delta S has to be less than 0, right? Because temperature is always a positive quantity, so negative, right? So this minus sign means that delta S here has to be less than 0, okay? So both delta H and delta S have to be less than 0, right? Have to be negative for this process to be spontaneous at low temperatures, but non-spontaneous at high temperatures. Questions about this? Would be an example of something that's spontaneous at low temperatures, but not at high temperatures.
Water.
Yeah, right, there you go. Freezing of water, right? The simplest types of things, right? Think of phase changes often as what I do for these type of problems, right? If I think of a phase change, right? Liquid water freezing is only spontaneous at low temperatures, right? Well, the freezing of water, right, is an exothermic process, right? Going from a liquid to a solid is exothermic. You're giving off heat, right? Because you're gaining all these favorable intermolecular forces, okay? So it's an exothermic process. Heat is given off to the surroundings, okay? And then, right, you're getting system, so the entropy change should also be less than 0, right? And so, right, that is consistent with our observations based off of the math, right? That enthalpy and entropy are both negative for this process that's only spontaneous at lower temperatures. Okay. Right. And again, right, part of the reason, this, going from a liquid to solid is exothermic, just like going from a gas to a liquid is an exothermic process, right? Which is why steam burns you so much, not because of how hot the steam is, but because when it condenses on your arm, it releases a lot of energy, right? Or your hand or whatever, right? All right. So which of the following statements or conditions is true of an equilibrium process? That it is reversible at delta G equals 0 if temperature and pressure are constant, if delta S of the universe is equal to 0. And one of these things true, two of these are true, all three are true, or none. All right, so what do people think?
All of the above.
So you got some all of the above, right? So reversible, right? A reversible process, right, by definition is a process that maintains equilibrium during the entire change, okay? So an equilibrium process is a reversible process, okay? Right? So again, you can think of a phase change occurring at equilibrium, right, at the transition temperature, right? You have liquid water at 0 degrees Celsius. That water can go to ice, and that ice can go to liquid, and they can go back and forth freely as much as they want, right? That change is reversible, okay? And those phases are at equilibrium, right? So an equilibrium process is a reversible process, okay? Okay. Right, a reversible process, right, we've talked about before, has an entropy change of the universe equal to 0, right? So a process that's done at equilibrium has an entropy change of the universe equal to 0. And then under constant temperature and pressure conditions, right, the Gibbs free energy is related, is equal but opposite sign to the entropy change of the universe. The entropy change of the universe is equal to 0, and the Gibbs free energy is equal to 0 under constant temperature pressure conditions. And so all three of those things will be true, okay? Now, if I just said delta G equals 0 in general, that is not necessarily true, because again, delta G only is equal and opposite sign to the entropy change of the universe under constant temperature pressure conditions. Okay? Otherwise, they are not related to each other, and so the Gibbs free energy change for some equilibrium process might not be 0 if temperature and pressure are not equal to constant, or not constant, right? Questions? All right. So talking a little bit more about Helmholtz free energy, Gibbs free energy. So again, Helmholtz free energy, Gibbs free energy can tell us about whether or not a process is spontaneous under constant temperature and volume or constant temperature and pressure conditions. But there's also some other stuff they can tell us about, and it's related with the maximum amount of work that you can get out of some change in state. Okay? So we start with the Clausius inequality, okay, which says, right, that the entropy change of some process is always greater than or equal to the heat transfer divided by temperature, okay, right, which that entropy change, right, is related with the reversible heat transfer, okay. So take the Clausius inequality, multiply everything by the temperature, right? So you have temperature times the change in entropy is always greater than or equal to the heat transferred, okay? And we use the first law of thermodynamics, du equals dw plus dq, okay? And so plugging in dq, right, is always less than or equal to TdS, okay? You will get that du is always less than or equal to dw plus TdS, okay? Right, so TdS is always greater than or equal to dq. So if I plug TdS into here, then the right side of this equation is got to always be greater than or equal to u. Okay? That kind of makes sense as to how that equality came in here, right? Right, because du equals dw plus dq. Except now I'm going to substitute in for dq some quantity that is equal or greater than dq. So that means du has to always be less than or equal to that new quantity. Okay. So, and then here, all I'm doing is I'm rearranging things, right? I'm going to subtract TdS onto the other side, and then I'm just going to flip my equation. Okay? So I can do that. I end up with dw is always greater than or equal to du minus TdS. Okay. Questions so far? All right. So calling here, right, at constant temperature, okay, we know that dA is equal to du minus TdS, okay? And so just using that, we get, right, that dW is greater than or equal to dA, okay, right, at constant temperature conditions, right? So assuming constant temperature, right, dW is greater than or equal to dA, okay, multiplying everything by -1, okay, you'll get negative dW is always less than or equal to negative dA then, okay, multiplying by -1 flips the orientation of that greater than sign, right? And then we use the fact that the work in the surroundings is just equal to negative the work in the system to get that the work in the surroundings is always less than or equal to -dA, okay? And so, you know, sort of integrating that equation, if you will, right, you'd get the amount of work in the surroundings that can be done is always less than or equal to minus delta A, okay? Right, which is telling you, right, that negative delta A is always greater than or equal to the work in the surroundings, right? So the work in the surroundings can be at most equal to that Helmholtz free energy change, okay, in your system, right? So if I have some process, right, and I want to know what is the maximum amount of work that I can potentially get out, okay, of that process in terms of work that's done on the surroundings. So that maximum amount of work that I can get out is related with negative the Helmholtz free energy. Okay. Similar, we can show for non-expansion work, okay, right? So here, so looking at the maximum work on the surroundings. Here, we're going to look at the maximum amount of non-expansion work. So EX here standing for extra work. So to do this, we start with the definition of enthalpy, okay? Write out what the total differential of that enthalpy is by just taking dH du plus d of PB, which is PdV plus VdP. Right, plugging in for the first law of thermodynamics, okay, of du equaling dq plus dw expansion plus dw extra. So E here is extra work. Okay. You know, for reversible change, that expansion work minus PdV. Okay. And then the reversible heat transfer is just TdS. So if we use those, if we assume kind of a reversible process, okay, substitute in for these things into equation 3 here, okay, you'll see that we have minus PdV plus PdV, so those things will cancel out, and we'll get dH reversible is equal to TdS plus dW extra reversible plus VdP, okay, right? So we have this for dH reversible, okay. H is the state function. So even though we solved this change in enthalpy for a reversible process, that change in enthalpy would be the same whether or not the process was actually done reversibly. Okay. So this works for a non-reversible process as well. Okay. And then using the definition of Gibbs free energy, right? dG is dH minus TdS minus SdT. So plug in what we found for what dH is. Of TdS plus dW reversible plus VdP, okay, right? The TdS and cancels with each other, right? And you're left with dW, right, extra reversible plus VdP minus SdT. We assume we have some constant temperature pressure process, then change in temperature 0, right? Change in pressure 0. So that just leaves us with dG is equal to dW extra reversible. Take the negative of both sides. So minus change in Gibbs free energy is equal to the work done on the surroundings, extra work done on the surroundings reversibly. And then, right here, right? But right, in general, right, the reversible work is always greater than or equal to the irreversible work, right? We've shown that many times, right, that the reversible work is always greater than or equal to the irreversible work, okay? So this gives us our maximum value, okay? So negative delta G is going to be the maximum amount of non-expansion work that can be done for constant temperature pressure systems on the surroundings, okay? right? Because the non-reversible work is always less than that reversible work, and the reversible work equals minus delta G. So delta G represents our maximum non-expansion work, okay? And so this is why, for example, if you wanted to know what is the maximum amount of charge I could get out of a battery, right? Say a lithium-ion battery or something like that, right? I would want to calculate what is the total free energy change for discharging that entire battery, right? For allowing that electrochemical reaction to go to completion, right? Until it stops, what is the total free energy change of that process? And that can tell me what is the total amount of power that my battery could provide, right, for that system, okay? It's the same type, this is also, if you want to look at the amount of, say, chemical work or other things like that you can get out of your body, right, out of certain processes that take place in your body, right, you can look at this free energy change, okay? So, right, so calculating this non-expansion work is often useful in electrochemistry, okay, as well as in biology as well. So, questions about how we got these two equations here? Right. How we get them? No. No. So again, everything in this class, right, that we derive, you don't have to memorize how we derive them. It's good to know the restrictions, right, on any equation. So that's the thing. You don't have to memorize how to derive them, but you do need to kind of remember, okay, this relationship is useful under these conditions, right? What are the conditions that these relationships are useful for? Okay. So again, here, this maximum work is assuming constant temperature pressure conditions, right? Which again, most like chemical reactions are constant temperature pressure conditions, so it's very useful in general. Okay, right? The Helmholtz free energy, right? Here we assume constant temperature conditions. Okay. Nope. Doesn't have to be constant volume. So actually, a lot of times Helmholtz free energy is used to get the maximum amount of expansion work they could potentially get out of a process. And so yeah. Right, because if you have no extra work that's potentially being done, then the only work is expansion work. So often Helmholtz free energy can tell you about the maximum amount of expansion work, right? Because again, the Helmholtz free energy isn't like defined only under constant temperature volume conditions, right? It's just that it's only related with entropy of the universe under constant temperature volume conditions, right? But you know, again, at constant temperature conditions, it can be used to tell you about the maximum amount of work you can get on the surroundings. So if an oxidation reduction reaction has an enthalpy change as follows, right? The maximum amount of electrical work the redox cell can do on its surroundings is equal to 3,475 kilojoules at 298 Kelvin. What is delta S for the reaction in units of kilojoules per Kelvin? All right. I don't have any thoughts? All right. B's, some C's here. All right, so let me just write out stuff here, double page. All right, so these are kind of the things given in the problem, right? Maximum work here, kilojoules, right? Delta H and T, okay? Well, that maximum work, that 3,475 kilojoules, has to equal minus delta G, okay? Which that is negative delta H plus T delta S. So plugging in delta H here, that's going to be 3340 plus 298 times delta S. That equals 3475. So you just subtract 3475 onto the other side, divide by 298, you'll get delta S equals 0.453 kilojoules per Kelvin. Questions? All right. So here's an example of how this relates to biology, right? So how much energy is available for sustaining muscular and nervous activity from the combustion of 1 mole of glucose under standard metabolic conditions, 1 atmosphere. Okay. It's known that the combustion of glucose has an enthalpy change of 2,808 kilojoules, an entropy change of 182.4 joules per Kelvin for the combustion of 1 mole of glucose. All right. So how would I get this maximum amount of energy that's available for sustaining muscular and nervous activity? What do I need to calculate to get that? Delta G, right? I got to get the Gibbs free energy change, right? Which is equal to delta H minus T delta S, right? And we're just given delta H, delta S, and temperature. Yeah, no, I didn't switch over, but thank you for making sure. I was aware that I didn't switch it over because often I'm not. So, so I appreciate it. Right, delta S, right? I didn't switch over because I didn't write down the numbers, so I have no idea. Right, but delta S is given, temperatures given. I guess technically, right, you could argue, oh, but couldn't these change the temperature? I didn't explicitly state, right, but we're assuming temperature independence of enthalpy and entropy, right? I should have stated that in the problem, but, right, I mean, we're not given the information needed to calculate the temperature change of those things if we wanted to anyways, but yeah, right, so the temperature that we're dealing with is actually 37 degrees Celsius, right, not this 298. So we have to take that 37 degrees Celsius, convert it to Kelvin, multiply that by entropy change, convert that to kilojoules, because it was joules, and then add that, or subtract that from the enthalpy change, okay? Shoot. And what you'll get, you'll get is, so, there we go. And when you plug in those numbers, you'll get the Gibbs free energy change at around 2,751 kilojoules. Okay, so the maximum amount of work is just negative 2,751 kilojoules. Now, this actual number is not the actual number. Okay, for one, I'm pretty sure the burning of glucose is an exothermic process, not an endothermic process. I just made up numbers, throw in there. So, you know. Well, yeah, well, just don't quote this as like an accurate thing, because again, one, this is saying this is a non-spontaneous chemical reaction, right? Because under constant temperature pressure conditions, Gibbs free energy is positive. Okay, which again, I'm pretty sure that's not true. So again, I'm pretty sure that my made-up enthalpy change for this reaction is incorrect, and the entropy as well. I'm pretty sure I just made up the numbers, but yeah. So, but at least that's how you'd calculate it, right? Assuming you actually knew those numbers, right? But again, this again can tell you information about, right, how much energy is potentially available in something that you potentially your body could use to do certain things, right? That don't involve expanding and compressing gas. Right? All right, so. Last time we kind of talked about this, right? How to get Gibbs free energy changes for reactions. Okay, we did this example here, right? And we did this example here as well. Okay, talked about it at the end of class, calculating the delta G for the chemical reaction. Okay, at different temperatures, assuming enthalpy was or was not constant with temperature. Okay. So I won't really go over that again today. This we're going to actually talk more about Monday, so we're just going to kind of skip it today. And so, this isn't a bad thing. So there's this question here, but I also added on a bunch of questions, kind of talk about like different changes of state, and kind of just going over like, writing out what is some of the information we know and other things like that. I want to kind of get to. So we'll just quickly talk. We'll do that same approach for this problem, but we won't work out the numbers, right? So in this problem, I have 0.2 moles of an ideal gas. I expand it isothermally against a constant external pressure, 0.85 atmospheres, from 0.4 liters to 1.5 liters at 325 Kelvin. what is the work done for this process, and then what is the maximum non-expansion work on the surroundings, what is the maximum expansion work on the surroundings also. Okay. So what thermodynamic quantities is this question asking you to calculate? Yeah, so we need to get work, we need to get Helmholtz free energy and Gibbs free energy, right? So, how are we going to do this? So first, right, so I guess, I'm trying to think of how I have other questions up, right? So I guess one of the first things we can ask ourselves, right, is what is being held constant in this problem? What is constant, right? So temperature of our system is constant, okay? The external pressure is being held constant, okay? And while we don't often explicitly talk about it, right, the number of moles is also being held constant, right? Right, expanding compression gases, right, the number of moles is being held constant, okay, right? So those things are being held constant. So what's changing? What thermodynamic quantities, or wait, not even thermodynamic quantities, but what kind of variables, what state, temperature, pressure, volume, I'm trying to decide how to describe those things, right? But right, temperature, pressure, volume, number of moles, things like that. What are those things? What is changing for a system of those things? Pressure is, volume of our system is also changing, right? Expanding this gas, its pressure and volume are going to change, okay? Right? Right, and that's it. But again, think of the quantities like in your ideal gas law, P, V, N, and T, right? What are those things are being constant? What are those things being changed, right? And then the question is, what are the relevant, right? And then what are we being asked for? Right, we just talked about that. We asked for work. We're asking for negative delta G and negative delta A effectively, right? Because the maximum work being done, okay? I'll go over now to kind of what I'm writing down as we're talking about this, right? So again, things that are being held constant, temperature, the external pressure, number of moles, things that are changing, pressure and volume of your gas, right? And then asked for, we're asking for work, and we're asking for Gibbs free energy, Helmholtz free energy, okay? So what do I know? So then what are the kind of equations that are relevant, right? So what equations are relevant for work, right? If I'm trying to get work, what equations are relevant given these changing and constant things? Right, yeah, minus P external delta V, okay? Right? And then what about delta G? How do I get delta G, assuming these constant and changing things? How would I calculate that? What is Gibbs free energy equal to in general? Not change, but just Gibbs free energy is defined as, yeah, H minus TS, right? Under constant temperature conditions, right? A change Gibbs free energy is then delta H minus T delta S, right? Okay. So again, these are all state functions, G, H, and S. So assuming temperature is constant, right? Change in H will change in S will result in that change in delta G to that equation, right? And then delta A, right? Delta, right? So to get delta G and delta H, I need to find out what delta H, or sorry, delta A, sorry, this is A, right? To get delta G and delta A, I need to find out what delta H and delta U and delta S are, right? Okay. So again, we can start thinking equations, right? One, that, PV equals nRT, right? I guess we're assuming ideal gas, right? Again, unless you're told otherwise, assume ideal gas, right? So you always got the ideal gas equation, right? That's always a relevant equation that you can use to find some potential variable you don't know, right? Pressure, volume, or temperature, right? And then what equation is relevant for, say, delta H, right? Assuming these constant things and changing things. Okay. Cp delta T, right? As long as number of moles are being held constant, okay, delta H can be written as Cp delta T, okay? Right? Which again, since temperature is being held constant, we do know that that equals 0, right? Delta U, what relevant equations do we know? Yeah. Cv delta T, which will also equal 0. What other equation do we know for delta U? Yeah, Q plus W. So I'm writing these like off to the side. These are kind of true whenever, okay? I guess this is only true for ideal. This is true whenever, right? First law of thermodynamics always works, right? This is only ideal gas, but, right? So like these two equations assume the constant temperature, right? This assume the constant P external, okay? Right? And these two equations assume constant number of moles, okay? And ideal gas, right? And so, right? And then what about entropy? How would I get entropy change for something where temperature, P external, and N are being held constant? And R ln V final over V initial, right? And again, I can use that because that is the entropy change for a isothermal reversible change in state, right? And so since temperature is being held constant, I can use the isothermal reversible form of entropy, okay? Because again, that is true for a constant number of moles and constant temperature, okay? So those are all the relevant equations that we use that we can then use and plug in our numbers to calculate the quantities in the problem, okay? Yeah. Yep. So for this process, delta G and delta A will be equal to each other. Mm-hmm. All right. Okay. Right. And again, on the slides here, go through and plug in the numbers. You get the work that's done is minus 94.7 joules. You'll get the maximum amount of work possible is 715 joules, right? Which is definitely greater than the work that's actually done of 94.7. Because again, the work that's done is an irreversible process. It's always going to be less than or equal to the reversible work, 715 joules. All right. So we just kind of talked about, I guess, this process, right? Reversible, in this case, isothermal expansion. Okay. So let's go back to. So here, I'll give you guys a second to actually read the question. I already knew what was on the question because I wrote it this morning. Right. But so the question here is, how would I calculate like all these wonderful thermodynamic quantities, right, for the reversible isoexpansion 1 mole of an ideal gas from, say, at 275 Kelvin from 1 liter to 5 liters, right? How would I calculate those things, right? So again, right, I have a reversible isothermal expansion, okay? Right? So if I do this expansion reversibly isothermally, what changes from what I have here? Yeah, work changes because now the external pressure is not constant. External pressure is now changing, okay? And work is no longer P external delta V, right? Is equal to, yeah, final over V initial, right? And otherwise, everything else is the same, right? From that other problem, right? So the only thing that changed here was work because I did it irreversibly versus reversibly, right? But both questions had an isothermal change in state, right? It's a question of basically whether or not the external pressure was constant or changing. Okay. Questions about this? All right. All right, so we went over what's changing, what's constant, what equation should I use. Right, in this case, what's being asked for is everything. So, I'm not going to bother writing that out. Okay. All right. Now, same kind of question, right? How do I calculate all these amazing thermodynamic quantities, right? For 1 mole of an ideal gas that is heated under constant pressure and under mechanical equilibrium with the surroundings, that has a pressure of 1.3 atmospheres from 0.5 liters to 4.6 liters. Okay. If I could do like a split screen here, right? Okay. So let me just do it like this here. Are we this one, right? That's what we're talking about. Yes, there's the mouse. Here we go. Yeah, that's what we're talking about. So let me just copy over these questions to this slide. Okay. All right. So let's start with what's constant here. Right, so pressure, yeah, and P are being held constant here, right? Because we're told it's heated under constant pressure, so we know it's heated, the external pressure is constant, but we're also told, and under mechanical equilibrium, meaning that the external pressure and the internal pressure are the same, so those also have to be constant, okay? Right, so we know our pressures are constant, right? So again, this type of problem, you could imagine you're like heating a balloon, right? A balloon is always at constant pressure and always under mechanical equilibrium, right? So this problem is effectively like heating a gas inside a balloon, right? And what else is constant here? Moles, right? N, okay. So again, think of our quantities in our ideal gas law, N, P, V, and T. Right, so what's changing here, right, is then volume and temperature. Okay. So now, right, given kind of what's changing, what's being constant, right, what equation should I use, right? So let's go to the next slide for that. So let me copy these things over, right? Let me, because the people on Zoom are seeing this slide. All the people in class are seeing this. I want to just share this screen. So now I don't have to flip up, right? So what equation should I use, right? So let's start talking about things. Insert here, equation. All right, so work. Just start off listing things, right? Work. Right? Right, minus P external delta V. Right? I don't know. Right? We always have our ideal gas law, PV equals nRT. Okay? I will note in this problem, you are not told any temperatures. Right? So you need to use the ideal gas law to get those temperatures for the problems, right? Because you're told the external pressure, which equals your internal pressure. So you know the pressure of your gas, you know the volumes of your gas, you know the number of moles, so you can calculate the initial and final temperatures using the ideal gas law, right? Okay. Which again, to calculate those temperatures, we have to use the ideal gas law. We can't use any other relationship, right? What other things, right? Ask for like delta U equals Q plus W. This is most likely the equation we'll use to calculate heat, right? But we know that for internal energy. What else do we know for the internal energy? Yeah, we know it's equal to CV delta T here. Just start a new line for that. So it's not split. Okay. Right. Yeah, and actually this, you are correct. This time delta H is equal to Q because you're at constant external pressure and mechanical equilibrium. Thank you. That's actually a great point. And if you were to plug things in, you would arrive at that same thing. Right. she calculated what work is, what delta U is, and you use the first law of thermodynamics to get Q, you'd end up finding that that equals the same thing as delta H for this problem. So yeah. So even if you didn't realize that, which actually I didn't think about that myself, right? That Q equals delta H, you will get that same answer in the end. Okay. Okay. Let's see what else here. Actually, so for this one, what's changing? Volume and temperature is changing. So this one's actually, yeah, so I probably wouldn't ask for delta G for this question. Let's see here. So volume, temperature changing. We talked about, actually Monday, we will talk about how to get delta G for changing temperatures, assuming constant pressure, which is what this is. So yeah, so we haven't actually talked about how to get that yet. So to be continued, right? So delta, yeah, so delta, in this problem, I wouldn't actually ask for delta G and delta A, at least yet. So let's ignore those and just talk about delta S. How do I get delta S for this? What's being held constant here in my system? Pressure, right? So since one thing is being held constant, right, my entropy, I can assume a reversible pathway that connects the same initial and final states. If pressure is being held constant, I'd want to assume a constant pressure reversible pathway. So as the entropy change for a constant pressure reversible path? Yeah. Right. I think that's, yeah, again, ignoring delta G and delta A for this question, that is, yeah, everything. Okay. Right. And then another equation that could potentially end up being useful, right? Depending on, like, in this problem, I didn't give, like, oops. Right. The relationship between CV and CP for an ideal gas. I do state it's an ideal gas. I don't say it's like a monatomic ideal gas with the CV equal to 3/2 R or something like that, right? So, you know, potentially, you know, that would need to be given to solve this problem. So there's a slight bit of information not given, but yeah, but we can then use that relationship between CP and CV. Okay? All right. Right. Shoot. I have a bunch of these that we don't have time to go over all of them. Yep.
Quick question on the one we did earlier, where we actually moved the numbers.
Oh, yeah.
So, yeah. So in that case, my non-expansive work and my expansive work maximum equal. Why do we have it? Yeah, just in general.
Basically, because for here, let's see, so you have an ideal gas that's being held at constant temperature. Okay. So essentially, what that is just saying is for this process, right? Those maximums are equal, but they will not occur at say the same time, right? That if I want to get the maximum amount of expansion work, then there better not be any type of non-expansion work going on. If I want to get the maximum amount of non-expansion work, I better not be doing any expanding of any gases, right, for that to occur, right? But that's just saying that this ideal gas has some maximum amount of work that it can provide. It can either go all into expansion or all into non-expansion processes. Okay. Let's see here. So yeah, we have a bunch of other examples here. We just, again, we don't have the time to go over this today. We'll see if kind of next week, maybe Monday, I'll throw these at the end of the slides, see if we have some more time to get to them. But otherwise, I'll try to I'll at least add in like this stuff to each of these questions, and I'll post this slide. Maybe I'll post it as some extra kind of PDF or something like that, not linked to lectures. But add that to the Canvas website. Again, it's, and I'm doing this here is just kind of hopefully, will end up being helpful for people, right? When approaching these problems on homework and on exams, right? To be able to, get some more practice of just sitting down and thinking what's happening in the problem, right? Because that's what I'm concerned about for this class, not whether or not once you have these relevant equations, can you plug in the right numbers to solve these things, right, in your calculator, blah, 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 right? That's great if you can do it, but that's not what we're trying to learn in this class, right? We're trying to learn in this class, right, given some process, something that's happening in the lab, right? Here things are changing, here things are being held constant, right? If I wanted to know some of these things, how would I calculate, right? Right, given whatever information is measured in the lab, okay? And so, yeah, so that's what we care about, right? That's what we're trying to learn in this class. And so, so I'll post this, and we'll see if we have time on Monday to kind of do some more of these in class. But otherwise, you're welcome after I post this, right, to do it yourself, right? Take a look at the question, write down these, things, write down what's changing, what's constant, what equations do I need to know, right? Okay, and then see, did you get the same type of things that I have written down in the problems? Yeah. I will see you guys on Monday. And turn in your homework either up here or when you leave at the table in the back. Either place is fine by me. Okay.
If it's in, I'm gonna be. If it's in, I'm gonna cry. I'm gonna cry.
Any questions real quick on on Zoom here? I don't even know how many people are still here. There's one other person. All right, well, I'm just going to end the Zoom session. So.